Good morning, Academy for Advanced Study students. This is Miss Rains. I am actually doing my video for stoichiometry. Same thing that you've seen the other day, just slightly different explanation. Um, the whole process centers around using the units and using dimensional analysis. So that's kind of a term that I keep referring to when I'm scoring and commenting back to your virtual practice. So we're continuing with our standard 3D, which is solving different types of stoichiometric problems. We will still focus on significant figures, even though we may not be assessing on it. And our goal today is to calculate any amount of product or reactant of a substance in a chemical equation with any starting value. So remember that stoichiometry is the calculation of quantities in a chemical reaction. When you know one of the substances, you can determine the amount of any of the other substances. So the quantity could be grams, liters, molecules, atoms, ions, formula units, particles. There's all kinds of different things that it can be. It does come down to some four basic conversions. So remember these first three from the beginning of this unit. The fact that 1 mole, ah, so the fact that my 1 mole equals my molar mass. Remember, your molar mass is the sum of atomic masses. Anytime you see grams in the problem, you're going to have to do an extra calculation. You're going to have to refer to the periodic table and find the mass of the substance you're working with. So the second equation, that 1 mole equals 22.4 liters. Remember, that's dealing with our volume. We're making the assumption that it is for a gas, and the gas is at STP, standard temperature and pressure. Technically, we don't know how to deal with anything not at STP, so whether I say it or not, for now, just assume that it is. And the third equation is Avogadro's number. It's showing the relationship between a mole and the number of particles. Remember, a particle can be an atom, it can be an ion, it can be a formula unit, um, or it could be a particle. So any of those are interchangeable. General rule of thumb is if it's not a volume, if it's not a mass, it's not a mole, it's a particle. So last but not least is this mole ratio, our equality statement that relates the moles of any two substances in the equation. Remember that my mole ratio uses my coefficients. So in order to use this piece, I have to have the coefficients. I got to have that balanced chemical equation. Some terminology so that we're all speaking the same language here. Chemists like to use the term theoretical yield. I'll ask you sometimes to find the theoretical yield. Theoretical yield is just a fancy way of saying how much do you expect to make. So it's the maximum amount of product that can form during a reaction. Think about if I fix a box of muffin mix. According to the back of the box, can't talk, I should get 12 muffins out of my muffin mix. But whenever I make blueberry muffins, I always get 13. And because I'm a chocoholic, whenever I make chocolate chip muffins, I always get 11. So my theoretical yield is what I should have gotten 12, but I don't actually get that when I go and make the muffins. Kind of the same idea. Theoretical is your calculations. It's what you think you're going to make. Anything that you calculate. Dyslexic moment. So we're going to assume Miss Rains can spell calculate. Sorry. So anytime you're doing calculation, you're calculating theoretical yield for the product, whether we ask for it or not. So actual yields, we won't, unfortunately, get to see this year due to, coronavirus and the remote learning situation. But the actual yield is what you physically make in the lab. I make my box of muffin mix and I physically get X amount of muffins. So there are some general steps to doing stoichiometric conversions. If you're not given moles, the first step is always to get to moles. So when in doubt, mole it out. Whatever that starting unit is, you're going to turn it into moles. So if it's grams, you're going to use your molar mass. If it's liters, you're going to use the 22.4. And if it's any of my particles, you're going to use Avogadro's number. Once you've got moles, then you're going to use your mole ratio. So this is always the middle part of multi-step conversions. When I'm switching from one substance to another, I'm going to have to use my coefficients in my mole A and my mole B. Last but not least is going to be to find whatever your desired unit is. So you're going to be using one of these first three conversions a second time. It will be with a different substance. So you might have to find the molar mass of substance B and determine what that is, or it might be the volume for substance B, or the number of particles for substance B. It varies from problem to problem, but the nice thing is it's pretty predictable. You get moles, switch substances, and then get whatever the problem asks for. So let's look for, not quite. So a couple of things that you want to remember. First and foremost, you got to have that balanced chemical equation. If you don't have a balanced chemical equation, you cannot do stoichiometry. So you're going to have to balance it. The coefficients are only used in the mole ratio. That's the only time that I'm going to use that coefficient. Any other time, mole is going to be a 1. So it's saying 1 mole unless I'm switching substances, unless I'm switching from water to hydrogen, for example. The mole ratio is the only place that your substances can change. As you're doing these conversions, you only switch one thing at a time. So there's no way that you can switch from grams of one substance to grams of a different substance. You have to go through the whole 3 steps. I can't go from particles of hydrofluoric acid to grams of sodium chloride because I'm switching 2 different things at the same time. And also, whatever your given number, that starting amount in the problem is only ever written one time. And it always goes at the beginning. It drives the rest of your conversions. It lets you know how you're going to set up everything else. Last but not least, if you've got a problem that talks about an excess reactant, it's just something that you have too much of. And if you've got too much of it, it does not affect your calculation. So in a sense, you can always cross out your excess. So, I know I'm making muffin mixes. I got 3 boxes of muffin mixes and 3 dozen eggs. Well, I got too many eggs. So my eggs are not going to determine how many muffins I can make. It's going to be my 3 boxes of muffin mixes. But we like to use that word as a chemist doing an actual in-lab experiment. It's nice to know that I have too much oxygen because it can drive the experiment. It can determine what I make. But for calculations, it doesn't really affect it. So let's look at a couple examples. Notice right now I'm giving to you the balanced chemical equations. I'm not going to always show that 1 in front of the nitrogen because remember 1s are assumed. So looking at my first example, I am starting with grams. So since I know I'm starting with grams, I'm going to use this relationship here. That means I'm going to need the molar mass of NH3. So I'm going to have to use my periodic table and I'm going to have to add up 3 hydrogens plus 1 nitrogen, and I'll get the molar mass of my NH3. Either way, once I get that molar mass, when I'm setting up my conversion, the first thing that you want to write is your given number and your given unit. That's going to be the first thing that hits my page because it's going to drive the next step. So when I look at this given number and this given unit, grams is telling me that in order to cancel out, I'm going to have to put my grams on bottom. If grams is on bottom, my equality statement tells me that moles has to go on top. Now, get in the habit of writing your chemical formulas. It will save your sanity along the way. The relationship between grams and moles, well, 1 mole equals 17.04 grams. Remember, I did not make up that number 17. I got it from the periodic table. So I could physically show the grams canceling out and show that I'm left with moles. I typically don't because it starts to look a little bit messy and it kind of drives me a little batty, but you can. But this lets me know that I'm now at moles of NH3. So when in doubt, mole it out. Well, I don't want NH3. The problem is asking me for grams of nitrogen. But I can't just jump from moles of one substance to grams of something else. I'm going to now have to use my mole ratio. My second step in a multi-part conversion is going to be that mole ratio. So I got to figure out what I'm getting rid of because that goes on bottom. Again, your units guide your dimensional analysis. So mole has to go on bottom, but it's not just mole, it's mole of NH3. It's what I'm trying to get rid of. Whatever you're getting rid of goes on bottom. Whatever you're going to goes on top. So I'm trying to go ultimately to nitrogen. So I'm going to have to first go to moles of nitrogen. Since I've got a mole and a mole, that means my numbers come from my coefficients. So I'm going to have to look at my coefficients to, oops, have to look at my coefficients to determine those numbers. And because me and my stylist are not getting along, you've already seen the last step, which is to get to grams. So where did Miss Rains get that 28.02 grams from? Well, I didn't make it up. I looked at the periodic table. The molar mass of one nitrogen, sorry, the atomic mass of one N is 14.02, but we're looking at two nitrogen, so that's where I got the 28 from. So if I had a Casio calculator, it would make my life a lot easier to type this in with fractions. I don't necessarily have to, but it makes the math a little bit more mistake proof. If I don't, I have to know that anything on the bottom is being divided and anything on the top is being multiplied. If you're having calculator issues, please hop into the Google Meets to get some extra help from Ms. Rains. So looking at the second example, we're going to kind of try a slightly different strategy with this. We know we're starting with grams of ammonia, and I don't have a unit here, so I'm going to wait till I click to see what that unit is. But I could set up a plan. So how do I plan on approaching this problem? Well, I know I got to go from grams to moles, so that's going to have to be my first step. Then I'm going to have to switch substances, so moles of NH3 to moles of hydrogen. That's going to be my second step. And my last but not least is to get rid of my moles of hydrogen and to go to whatever my desired unit is. And in this case, apparently it is grams. So how did we go about setting that up? Well, I wrote my original number and its unit, so my 48.38 grams of NH3. My unit determined that since I started with grams, grams has to go on bottom. So if grams is on bottom, this tells me that I must put 1 mole on top. I've done that part, so my next part is to switch substances. So now I've got to get rid of that NH3. So in order to get rid of NH3, it has to go on the bottom. My coefficients are used anytime I'm switching substances. So I know I have to use the 2 because I'm using NH3, and I know I have to use the 3 because I'm going to hydrogen. 3 goes on top. Last but not least, I've got to get to my grams of hydrogen. So that 2.02 came from the periodic table. It's 2 times my 1.01. You don't necessarily have to show your molar mass calculations. I encourage you to show it somewhere on the side, especially if you're still having issues with finding molar mass. It'll help me find your mistakes. Handy dandy calculator. I type in 48.38 gram, 48.38 divided by 17.04 times 3 divided by 2 times 2.02. Or if I've got my Cassie, I'll just plug it in using the fractions. And I get 8.603. Now our standard does talk about significant figures. So if we look back at our starting numbers for both of these, they had 4 numbers. Notice this 0 is sandwiched between the other 2 numbers, so it is significant. So my answer does have the right number of numbers. Alrighty, so let's look at example number 3. This particular problem, we can see that we are clearly starting with grams of ammonia, grams of NH3, and I'm trying to figure out what I'm ending up with. So I can see that I'm ending up with liters of nitrogen. Sometimes it might ask you for volume of the nitrogen, but remember, volume and liters are interchangeable. So I could set up my plan to determine what path I need to take. I can see that I'm not starting with moles, so that means I've got to mole it out. I've got to go from grams to moles. Once I have my moles, then I'm going to have to switch my substances. I'm going to have to get rid of my ammonia, and I'm going to have to go to moles of nitrogen. My last part, my last piece is going to now be to get rid of moles of nitrogen and to go to liters of nitrogen. So I've got a general game plan. I can actually go ahead and jump into my conversion. The first thing I'm going to write is the number and the unit that we started with. So my given number, my given unit. This will set up my conversion. This lets me know that since I started with grams, grams must go on bottom. If grams is on bottom, my equality statement tells me that mole must go on top. So I can see easily in my equality statements that the relationship is 1 mole and molar mass. Pardon me. It doesn't give me a molar mass, so therefore I got to remember to find that molar mass. So I've got to add up my atomic masses. I need my 3 hydrogens plus my 1 nitrogen to get the molar mass of ammonia. I've already shown this for one of the problems in the set. I wouldn't necessarily have to show it again, but since this is a different slide, I'm showing it for you guys again. So that 17.04 that you see on the bottom, I don't just make up. It literally comes from that periodic table. It is the mass of 1 mole of that substance. Now, we don't have a mole. We got 48 grams. So I can show that my grams are canceling out. I typically don't because it gets a little messy, but you could. And that lets me see that I've got moles of NH3 left. So I don't want moles, I want liters. And I don't even want NH3, I want nitrogen. So this means I've got to switch my substances. So moles of NH3 is what I'm trying to get rid of, therefore it has to go on bottom. Moles of nitrogen is my next step. So getting rid of the NH3, I'm going to the nitrogen, and since it's the mole ratio, I have to remember that my numbers come from my coefficients. So it's going to be a 2 on bottom and a 1 on top. My middle step in a multi-step conversion is always going to be that mole ratio. So got to switch my substances here. Now that I've gotten rid of my moles of ammonia, I can see that I have left is my moles of nitrogen. But the problem doesn't ask for moles of nitrogen, it asks for liters. So what I'm getting rid of goes on bottom, what I'm going to goes on top. I'm getting rid of moles of nitrogen, and I'm going to liters of nitrogen. So if liters is on top, according to my second relationship, 22.4 must be on top. If moles on bottom, it's got to be 1 mole. So handy dandy calculator, I could type this all in, and my calculator would give me 31.8, but the calculator doesn't know about significant figures. And if we look at our original number, it had 4 significant figures because they're all real numbers, non-zero numbers. So that means this answer has to have 4. So I'm going to add a 0 at the end because remember, zeros at the end after the decimal are significant. This lets me have my value being as precise as it started out. I didn't lose any significance in that. So one last example. This one is not to volume, it's actually to molecules. So find your numbers, find your units, and that will guide your problem. Some students get tripped up with the fact that it says theoretical yield, but remember, theoretical yield is just a fancy way of saying how much you plan on making. So it's an easy way to approach problems with extra words is kind of like I said a second ago. Find your units. Once you've got your units, it will let you know what is important in the problem. So develop a plan. I know that I'm starting with grams and I got to get to moles because if I don't have moles, I've got to mole it out. Once I have my moles, I'm going to switch substances. And for my last step, I'm going to get rid of moles and I'm going to go to molecules. So remember, molecule is a type of particle. That means I'm going to use my Avogadro's number. Please don't use MOL to abbreviate molecule. It tends to get a little confusing. I like to use MLC, but as long as it's not MOL, I don't particularly care. So we're going to start our problem like normal. We've got our 68.92 grams of NH3. And I know that I'm going to have to get rid of grams of NH3. So that's going to have to go on the bottom of the first fraction. Remember that 17 I got from the molar mass. I now have to get rid of my ammonia, moles of ammonia. So I'm going to use my mole ratio. Where did Miss Rains get these numbers from? Remember, they come from those coefficients. Those coefficients guide those particular problems. And last but not least, I'm trying to get to molecules, so I'm going to use my Avogadro's number. It's what I'm trying to go to, so it's going to be on top. So 6.02 times 10 to the 23rd. I'm trying to get rid of moles of hydrogen. I can actually show it being canceled out. And that means that 1 mole has to go on bottom. Type it all into my calculator, and it should give me scientific notation, simply because it's dealing with such a large number. Remember, we don't mind big numbers, small numbers in science. Any kind of number is valid, but let's look at the number of numbers. Odds are the calculator actually gave me more than that, but my original value had 4 significant figures. So I know in these 4 examples, I have started with just the reactant each time, but really and truly, it does not matter what you start with. You can start with any substance in the equation and still get to the same answers, that same process no matter what. So let's look at an example where I'm not starting with my reactant. I need a balanced equation, so we're trying to make water. And I want to know how many liters of oxygen is needed to make 45.0 grams of water. So set up your plan. You know you got to get from grams to mole. You know you've got to switch your substances. So this time we're getting rid of water and we're going to oxygen, and I'm going to liters at the end. So setting up the conversion, still the same. You write your given number and unit, 45 grams of water. I know I'm getting rid of water, so it has to go on bottom. And from grams, I know I'm going to mole. So 1 mole equals the molar mass of the substance. If I don't already know that, I have to calculate it. So I'm going to go to the side and show that calculation. I've got 1 oxygen plus 2 hydrogens gives me 18.02 grams. So I did not just make that number up. It came from the periodic table. 18.02. So now that I've gotten to moles of water, I want to get rid of my moles of water, and I need to find my moles of oxygen. This is where my coefficients come into play. So what's my coefficient in front of the oxygen? Well, there's not a number, so it's that invisible 1. My coefficient in front of the water is 2. And last but not least, I'm trying to get 2 liters of oxygen. So I need to get rid of moles of oxygen, and I need to go to liters of oxygen. My equation sheet, my formula sheet tells me that 22.4 liters equals 1 mole. So handy dandy calculator, type that all in and it would let you know what it equals. So my calculator gives me 27.9689 and a whole bunch of numbers. But if I look at my original number, I can see that I started with 3 significant figures. So I'm going to take that 27.968, and I'm going to round it to 3 significant figures. So I know I'm going to keep the 27.9. I look next door. Remember, 5 or more raised is 4, so that 9 is going to have to round up to a 10 or to a 0. Since it's becoming a 0, I would actually write 28.0 liters of oxygen as my final answer. Remember, we're honors students, so we want to think about significant figures, whether or not we're going to see it on an assessment. You will see it again later in physics or even in college level chem. I hope this has been helpful. I'm going to post a second video showing a slightly different method using the mole map. For those of you who don't like the dimensional analysis, setting it up following the units, the map is a great resource. So watch that video if you're still confused. Have a nice day.